Hey people, Dan Isbell. He's the US Air Force person who saw a black triangle near Upper Heyford while he was flying F-111 nuclear capable attack aircraft. Remember, he told Chris Lito and I his story of that sighting. But when Chris and I talked to him, we went over his CV, what he did in life, and what Dan told us was after he left the US Air Force, because of his physics background, he got involved in building, training, teaching, and using directed energy weapons, even being based at the Starfire Laboratory near Kirtland Air Force Base in Albuquerque, New Mexico. I immediately said, "Hey, Dan, I'm interested in directed energy weapons sometime in the future. Would you come back and talk to us about it?" He said, "Well, it's very classified. And in fact, he does lecture to the US Air Force to give a kind of primer to flyers about laser and microwave weapons which might be deployed in their capabilities with their aircraft." Dan Isbell kindly agreed that he would actually share his secret primer into directed energy weapons that he teaches at the US Air Force to me. And here it is today. Brilliantly and understandably, Dan does not mention deployed or actual weapon systems that are in the arsenal today. He talks about how laser weapons work, how high-powered microweapons actually work. What is in this talk with Dan is gold dust. If you want the very, very best information from a man who used, teaches, and built and developed directed energy weapons, you can do no better, in my humble opinion, than listen to my conversation with Dan and what Dan Isbell is prepared to share today with you here on YouTube. It's gold dust. Listen to it, enjoy it, ask questions. Dan will get back to you in the comments. He won't discuss anything classified. Good man, Dan. I will help to point you in further directions. But if you're interested in lasers, high-powered microwaves, and what actually they do, you're in for a treat. Thank you, Dan. Hey, everybody. Guess who we've got? We've got Dan Isbell back. Hi, Dan. It's really...
Hi.
Hi, it's an honor to have you back. You'll remember Dan told us his amazing UFO story at Upper Heyford when he was an F-111 pilot. But Dan has done a lot of other things in his life. Fighter pilot, and then a test pilot, and then after retiring from the US Air Force, he taught directed energy weapons, and that's what we're going to talk about today. What an honor. So hi, Dan. So what was that transition from the US Air Force into teaching in physics? Tell us about that.
Well, it was pretty seamless. I took off the uniform and just wore civilian clothes, and
Yeah.
um, they just basically recategorized my security clearance as now a civilian instead of an active duty colonel. And the first job I was requested to do was to be a technology integration consultant for the Air Force Research Lab, specifically the Directed Energy Lab out in Kirtland Air Force Base, New Mexico.
New Mexico, Albuquerque. But hang on a minute. You're one of these damn plane jockeys. What did you know about physics? Is that something that you'd already studied? Do you have a background in physics?
Yes, of course, as a aerospace engineer and many advanced degrees in various subjects.
Ah,
Um, and then my last duty assignment, as we'll see here in a moment, was in the Air Force Research Lab, and I was in charge of directed energy weapons
right.
for the Air Force Laboratory headquarters.
Do you
So
want to
I have a bit of
share with
an
our audience your amazing CV? I've seen it. It is pretty impressive. Dan has a PowerPoint slideshow that he can share some slides with today. See if you can share with the audience
Okay.
your what you've been up to during your amazing career.
Okay. Yes, give me just a moment.
Sure. So in blue, this is your Air Force career. I mean, the first word, Top Gun fighter pilot. You can't top that. Oh, yes, you can. Read down that list, and we're getting into, test squadron commanders and, even vehicle program manager of the F-22 program office. And then you start getting into directed energy weapons.
Yeah, so that's kind of it. I did the blue part. The blue words are my 26 years of active duty in the Air Force,
Right.
and then the black letters below that are things I did after retiring. So that's a sum total of 20 years of additional classified work done after retiring. So long and storied history in both those
Yeah.
the events. And really, it's up top, there's just a few, as I've abbreviated as much as I can. If you added up all the schools that the Air Force paid for and sent me through, it
Yeah.
would be 12 different colleges and universities. That includes the
Right.
military education.
Sure.
I've only included the things up there that had some accreditation and achieved other Master of Science degrees. So yeah,
Wow.
a lot of education, and they put all of that to use both during my active duty career
Yeah.
as well as my after active duty career.
That's very impressive that the DoD and Air Force could recognize such talent in academia as well as flying skills. Although, look at this picture. There's Dan sitting in it's an F-16. What's special about that picture, Dan? Where is it?
Yeah, so that's the F-16 that when I was in the 514th Flight Test Squadron as the commander, this
Oh, yeah.
part,
Yeah.
we had a specific white painted with orange tips test aircraft, never had a gun in it. It was designed to do flight tests
Mhm.
for Block 10 and follow on basically the A and B models of the F-16.
Yep.
And that was our Precious airplane called Little Precious.
Oh,
It was little because it was much lighter because it never had a gun in it.
right.
And it was precious because it was so well maintained. It had never been in combat. It came straight from the factory that at the time was General Dynamics, Fort Worth, Texas.
Wow.
Came straight there, painted up at Edwards Air Force Base to match other developmental test aircraft, and then stationed at Hill Air Force Base. And our test unit was a remote detachment from Edwards Air Force Base, California, the Air Force Flight Test Center.
And this picture is you sitting in a museum?
Yeah, it's now fully restored. It was on a pedestal for a while, but
Oh,
then it got kind of, over the years, it needed a new paint job because of being out there in the ice and the snow and the storms. So, and a
sure.
lot of blowing dust. So they recaptured it back into the Hill Aerospace Museum. They totally restored it. And when they did, they asked me to come out and give a plane talk, which I did, and then they had it opened up and had a ladder there so I could climb up inside.
Oh,
The auditorium was filled to overflowing because people from the local community really remembered that unique looking white and orange F-16.
right.
So they missed it when it was no longer flying, and so when the word went out about that we're going to have a special presentation about it, lots of locals from the community around Hill Air Force Base came out to listen to
Oh,
my talk and to see me in the airplane. So we had them come and gather around the airplane
right.
while in the cockpit, and they could ask all kinds of questions while they oohed and awed over the freshly painted, perfectly looking like brand new airplane. And
Bet.
so that's me sitting there that day in my flight jacket many years after I last flew it. We retired that airplane in 1995 by direction of the Base Realignment and Closure Commission.
Right.
And, um, and so that was my last flight in Little Precious. I continued to fly for the depot and do functional check flights for the depot for the next 2 years as we downsized our squadron
Right.
into that job. But Yeah, it's a precious memory, and that's me.
Oh, oh, I wish you could take it home. Yeah, we could fly it. We could fly it out of my local airport. Mind you, I think the fuel might be a bit expensive, but yeah, oh, what a
Yeah.
fantastic memory. Okay, let's go back full screen and let's talk about what we're going to talk about today, viewers, because it's absolutely fascinating. Hey, everybody, back full screen. Today we're going to talk about the Dan Dare ray gun. Well, not really, but we're going to talk about directed energy weapons, also known as DEW. Um, Dan knows a lot about them. Dan has worked with them, but we're going to operationally, but we're going to talk today more about the physics of them and about the concept. We're not going to touch on anything deployed weapon systems, but we're going to talk about the concept. We're very strict on that. You can ask Dan, and he can refuse to answer your direct questions. But let's talk about generally. I mean, it's Dan. It's always been a dream from science fiction comics that we could have a ray gun or even a Tesla death ray. But
Yeah.
I mean, do these things work? I mean, it's great because you don't fire bullets; you fire energy. So, what's the history of this, and does it work?
Yeah, well, the history is long and storied, and it does work, and it's advanced tremendously in the last 20 years.
Mm,
And, the United States and many of our NATO country partners, as well as some of our maybe not so neighborly, maybe Russia and China, for instance, they have also done a lot of work on this. So
right.
it's not something we can claim sole propriety on, but the research has been very intense over the years, and it has achieved some remarkable successes. So
Where did
today,
it all start? I mean, what's the earliest that you've ever heard of actually a weapon system that would be an energy weapon? Have you any?
well, in the laboratory, it started shortly after the discovery of what a laser would be, and we'll define that better.
Right.
Um, but in terms of directed energy that we now refer to as high power microwave, which is kind of the
Mm,
standard generic term that covers a lot of the electromagnetic spectrum below where the lasers would be.
right.
And and you can think of the fact that there are radars since World War II. Radar detection and ranging, radio detection and ranging is
Right.
what radar stands for.
Sure.
And we learned pretty early on that doing electronic warfare to try to jam an enemy
Mm,
radar was another way of trying to hide our forces so they couldn't get a weapons track solution on them
right.
by jamming them. So electronic warfare has been around since at least the Vietnam War.
Oh,
And
they had it in World War II. I mean, they
yeah,
had aspects of it, like, window dropping,
yeah,
things like that, and also, countermeasures, friend and foe devices were all. I mean, I'm a big fan of Robert Watson Watt. He's credited with radio direction finding, although that's kind of slightly dubious, but it might have come from somewhere else, but that's a big story. But he certainly didn't only do radio direction finding. There's lots of gadgets, good British word, that boffins, another good British word, made that did electronic warfare in World War II. I think there's a notion that men with handlebar mustaches looked down through their Bombay doors and pressed bombs away when we had incredibly sophisticated electronics in World War II. I mean, they were still
indeed.
electronics, they were still components, they were not IC integrated circuits, but they certainly did exist. Yeah,
Yeah, certainly the ground-based radars that were available in World War II. Um, the aircraft-based radars, not so much in World War II. For instance, the B-17,
right.
they had what's called the Norden bomb sight, which was a very highly calculated optical thing, and that's why they did precision bombing in daylight hours with the B-17s, and of course took enormous losses, combat
Mm,
losses doing that.
sure.
Uh, But yeah, it was.
Sorry, I have to interrupt. I love the Norden bomb sight because the Norden bomb sight, although it is an incredibly sophisticated piece of kit, I think there's over 24 alignment tools that a bomb aimer has to do before dropping the. I'm going to use the Norden bomb sight catchphrase: dropping the bomb in the pickle barrel. Before
Yeah,
you can do that, you need to be straight and level and not jigging and jogging around in
correct.
battle conditions. And in fact, it was very hard to use, I heard.
Yes, yes, but it did achieve certainly a better level of precision from
Mm,
medium altitudes where the B-17s were flying,
okay.
and it was the tactic used in World War II to try to overwhelm German industry with these
Uh,
massive raids of dropping bombs as precisely as possible. Now,
right.
it's not like modern day, laser range
No,
finding bombs or,
no.
the ones that ride the rail on a laser guided bombs.
Mm,
It's not certainly like the GPS aided munitions like JDAM, the Joint
say that.
Direct Attack munitions, but it was a level of sophistication beyond what was previously available, say, in World War One, where they're literally leaning over the side and hand dropping a bomb
Um,
out of an open cockpit of a biplane.
and the
That was,
concept, I love the birth of it, really, precision bombing, when I think it was a big Herzl or something airplane propeller manufacturer in Illinois got flooded out, and the training flights for Air Force Army pilots who broke props on landing tailwheel airplanes, they ran out of propellers. And somebody said, hang on a minute, if we could take out the man who makes the prisms for U-boats, precision bombing was a great
yeah,
idea.
yes, it indeed was, and so it's had a long time to evolve, and it's extraordinarily sophisticated now in a modern day fighter or bomber. Like if you take the B-2 or what's following it as the B-21, and you couple its stealth capability along with its very precise being ability to drop precision weapons on a target. Look at the most recent use of that with the
Right.
massive ordnance penetrators, which are 30,000 pound a piece, and what it did to Iran's nuclear refinement facilities,
Yeah,
enriching
right.
uranium to almost to weapons grade. So it's come a long way. I know when the F-117 was first used in combat, it had the first, significant amount of stealth type radar evasion. And so
Mm,
they were able to drop bombs in downtown Baghdad during the Iraq War, the first one, the Desert Storm,
yep.
and with impunity. They never
Right.
took a hit, never had a loss of aircraft in any of that. In fact, one of my old weapons systems officers who sat right seat with me in the F-111s at Upper Hayford, he later became, he went to pilot training. I used to let him drop bombs manually from the right seat. It was kind of, he was good. He was good
Go.
flying the airplane and so forth. So he got to go off to pilot training,
Mm.
and he became an F-15 pilot out of that.
Ah,
And
yeah.
then he disappeared, and we didn't know where he went. And later, he was the first person to drop a bomb out of an F-117 in Panama, or because
Mm,
of
sure.
Noriega,
Eureka.
took out his escape airplanes. And then he became the first guy to drop a bomb in Baghdad in Desert Storm. So
Ooh.
the
So
power of being,
he was a bombing, he had that bomb skill, but he also was a pilot. Great.
yeah, he was, that's a single seat airplane. And of course,
Right.
he became a very good F-15 pilot and then
Yeah.
was pulled out of that and sent off to what we now know as Tonopah, north of Area 51,
Oh
a
yeah.
part of that same range complex.
Mhm.
And they trained in total secrecy and couldn't tell anybody where they were or what they did. And it wasn't until after Desert Storm that the Air Force first debuted for public display an F-117. It
That's
was
right.
roped off with a large cordon, but it was displayed as part of an air show connected to a big military parade where we even had M1 Abrams tanks rolling down Constitution Avenue in Washington, D.C. Left
Right.
two big ruts, as you can imagine.
Big
But,
ruts.
General Norman Schwarzkopf marched at
Oh,
the
I
front,
remember. Right.
and it was quite a thing. They finally honored those Vietnam veterans at that
Good.
celebration. They had a special place down by the stage,
Right.
and I saw a lot of tears coming as they really
Oh, yeah.
spoke words of praise over them because,
Right,
they came
right.
back from that war. It wasn't their idea to go there, but they were all,
Mm-hmm.
they were all
Mm-hmm.
basically drafted to go do that. And then when they came back, people threw rotten eggs at them and called them baby killers and
No,
stuff.
no,
So
no, no. So wrong.
it was a horrible thing. But to finally see that come to
Yeah.
fruition and honor them
Mm.
uh, was a really good thing. And I was there for that. And I also went over to where they keep our Air Force One at Andrews Air Force Base in Maryland,
Sure.
not too far away, for the air show. And there was the F-117 out there. And I
Ah.
recognized the guy that used to fly in my right seat, who became an F-15 pilot and then the F-117 pilot. He's down there with the airplane talking to folks.
Oh,
And so his tactical call sign was Beast. And
good one.
yeah, so and we used to play some just, nickel dime quarter poker to while away the hours in when we were sitting alert.
Right.
And I can remember his favorite game was 727, and he always called it low side. So I'm back in the crowd. I haven't gone up enough for him to see me, but I yelled out over the people. I said, "Hey, Beast, 727, your deal, low side." And then I dropped down, and all of a sudden he didn't see me, and he goes, "Dana, where the hell are you?"
Yeah.
So
Great.
we had a good reunion there, and
Oh,
yeah. But the F-117 could precisely deliver 2,000-pound bombs out of its weapons bay
sure.
that were laser guided and would achieve, very, very small errors. It was
That's
centimeters
it.
of accuracy.
Changed warfare.
Yeah.
Funny story. So the F-117 eventually came to England, and I heard that it was coming to Mildenhall, Lakenheath air show, and so I went to see it. Whoa, it was impressive. It was just a roped off nothing.
Yeah.
The invisible plane, it was called. Oh, they were having a bit of a laugh, but yeah, it was hilarious. They didn't trust us Brits. I just had
Well,
Nick Cook on, who's was the aviation editor of Jane's Defense Weekly,
I
and
remember
he said
that.
it must have been at the same air show. He remembers seeing the very first F-117, and there was a step ladder, and he was allowed to go up it. And somebody whispered in his ear, "If you touch it, I'll kill you," because they didn't want anybody going anywhere near the ram coating.
Yeah. Yeah, it was called the Hopeless Diamond design.
Right.
And ironically, it was a Russian scientist who came up with this angular structure
Sure.
that could effectively create a radar cloak. And
Right.
and then it was Lockheed Skunk Works that decided, hey, maybe we can actually turn this into an airplane. And
Yeah.
they used the digital fly-by-wire system that was developed for the F-16, and
Ah,
they optimized the control laws to keep it stable because,
it was
I thought the
unstable.
thing,
Right.
yeah,
If
it
you
could
took your
not.
hands off, it would
Oh,
tumble.
you could not have flown it without that. And even with that, it had points in the envelope where it wasn't perfectly stable. So it
Oh,
was often called the wobbly goblin.
right.
Yeah. But it did the job, and pilots adapted to it quite
Mm-hmm.
well. And they actually put a lot of previous F-111 pilots into that aircraft over the years
Oh.
because their experience in low-level bomb dropping
Mm-hmm.
was quite on point. And
Right.
they optimized it so that they could fly it on autopilot and just worry about getting the laser where it needed to be, making sure the
Ah.
right target. And so they became sort of effectively weapons systems officers while they let the plane fly itself on autopilot for the actual bomb drop.
That's
But
great.
yeah.
I worked with Airbus Industries
Hmm.
on a film, as you do when you work in television, and they did this incredible counterintuitive autopilot. Originally, autopilot, I should say, fly-by-wire was an autopilot was where the plane computer would fly the aircraft and the pilot would be pilot monitoring. And all these French Airbus pilots hated it. They wanted to fly the plane, and in fact, it didn't reduce fatalities. In fact, they went up. So, just a bit like this is a bit of an engineering mindset of mine. Just a bit like vacuum train brakes. When the vacuum breaks, the brakes come on automatically, putting turning that idea on its head of blowing air to squeeze the brakes on. No,
Yeah.
when you release the vacuum, they go on. Fail safe.
Yeah.
Airbus did this counterintuitive thing and said, you know what? We'll let you fly the plane, and the computer will tell you when you're flying it badly. And that's what it. So you are flying, as you said, in an envelope, and
Mhm.
that's all it will basically allow you to do. But you're doing this or this, you know.
Yeah. Well, even the F-16 was the first aircraft that was statically, without the assistance of these computers, statically unstable
Oh, is it?
at about
Mm.
a 49% negative static margin, meaning that
Right.
to keep the pointy end
Yeah.
going frontwards, you had to have a lot of sensors and a feedback loop control system that would constantly be twitching the tails to keep the aircrafts in a stable forward point because otherwise it would diverge and
Was
flip
it?
over.
Oh.
And and that was used to the advantage for you to
Yeah.
go to a high G turn quicker
Right.
than any fighter in history.
Right.
If you look at F4s that preceded the F-16 or even F-111s or any aircraft before the F-16, when you pulled aft on the stick to get a high G turn, you could count one potato, two potato, three potato, four as the G's built up because you're fighting against its
Right.
static stability that's trying to keep the nose going forward. But compare that to the F-16. When you're sitting like we're sitting right now at one force of gravity,
Mm.
and you pull the side stick, 25 pounds of aft pressure on it, it only moved a tiny bit to give you a feedback. It didn't move originally. It was like grabbing a radiator pipe.
Oh, it was like
But they decided, well, no, we got to give them some movement.
a
We got
bit
to
of
actually
movement.
going
Right.
in. So when you do that pull, 1.3 seconds later, you go from 1G to the equivalent of 9.3 or sometimes higher in the later models, could go to 9.9 times the force of gravity. So now you as a pilot at almost 10 times your weight,
Yeah. Yeah.
your body, say, with all your flying gear, your harness, your
Mm.
stabilization stuff, and helmet, you probably weigh somewhere, let's just estimate 200 pounds total.
Sure.
Now you weigh 2,000 pounds.
2,000 pounds.
Yeah, so it did not work well because the brain uh, needs oxygen. Your heart's about 12 inches below the
Right.
brain, and it's got to pump blood up against 10 times the weight of that blood to keep oxygen in the brain. And if
Right.
you didn't do all kinds of, physical straining maneuvers with your muscles in your body, and it's a learned skill, and you had a G suit to help squeeze you a little bit to help put
Hmm.
something tightening your legs and help you push the blood back up to the brain. But if you didn't do that effectively, after you get to the 9+ Gs,
But
you have about 5 seconds of oxygen reserve in your brain, and then you go straight from conscious to fully unconscious.
whoa.
Won't get those symptoms that you would get in F4 where you start to have a little bit of tunnel vision and then you lose your color
Sure.
and then to ease off or whatever. No, you do this and then poof, that's called G-induced loss of consciousness. And there were some years where we lost as much as 13 perfectly good F-16s with perfectly healthy pilots who, once they went unconscious, the aircraft just did whatever it did.
Oh,
And we didn't have auto GCAS then, we do now. Automatic ground collision avoidance system is
yeah.
in the 16s of today, but we
Yeah.
didn't have it
Oh,
then. But yeah, so they started using the centrifuge as a precursor to
right.
determine, are you going to be able to do this? And you had to do that at that same, the centrifuge would actually respond the same way.
Sure.
So to mimic the F-16, and if you couldn't sustain yourself for at least 15 seconds at those 9G levels, and you passed out in the centrifuge, then yeah, you might go fly some other fighter, but you're not going to
Right.
fly the F-16.
Not
So
the F-16.
that was how we tried to guard that. It turned out that really tall, lanky, long distance runner kind of people, their blood pressure and heart rate was too low to ever make the jump fast enough.
Ah.
So the Air Force even restricted. I've done one marathon in my life, and then they said, no, no, no more distance running. You need to be working out with weights, and each squadron had their own weight training machines and do
Ah.
anaerobic rather than aerobic exercise. Because when you get like when I ran a marathon, I had my resting heart rate was 42, and I had a 90 over 60 blood pressure.
Oh,
That's a fatal formula for flying F-16. So I did that only while I was in a school for a year.
sure.
And then after I ran that and completed it, and then I went the other way, trying to, eat differently and
Yeah.
exercise differently to let my blood pressure and heart rate come up to a little bit more normal levels. But
Oh,
yeah,
flight ready levels.
yeah.
And maybe women are better as well. I don't know.
Well, I've flown with I was instructor pilot at test pilot school, and I flew with several women pilots that
Yeah.
did well. Although I didn't fly with them in F-16s when I was an instructor. We didn't have the F-16s in the curriculum yet.
Right.
But yeah, there's air show pilots now that are female that fly the F-35 and the
Yep.
F-16 and
Yep. Yeah.
F. I
All
don't know
my
if they're in
favorite
that.
CFIs in my Cessna days were all female instructors. They're very good.
Yeah,
Yeah,
yeah.
it was good. Well, okay, so oh, I love those stories. We could go on forever. Let's talk about ray guns and directed energy weapons. So the problem is, Dan, with directed energy, you're firing a energy beam out of something, if it's lasers, microwave, or whatever it is, peas. It's going to all the energy is going to dissipate. Tell us about the physics of energy and spectrum and the basic Newtonian physics and a bit of formula are what we're talking about.
Okay, great. If you don't mind, we'll share screens and
Yep.
I'll bring that up and we'll just talk our way through it. Ask any questions on any of these
Okay. I
slides as you
will.
need.
I will.
So I'm going to request then that we share this.
Here we are. What
Okay,
is a
good.
directed energy? DE. Right. Right.
So directed energy is just a beam of concentrated electromagnetic energy.
Okay.
Electromagnetic energy. And down on the bottom here, I have a colored scale. And it starts down here where, there's an audio spectrum like a piano keyboard or whatever that's the audio wavelengths, and they're well below the ones that we typically are doing. Then you have, things down here like power and telephone frequencies,
Right.
and then you get up into radio, and you move on up the spectrum. This shaded area that you encounter here is where high power microwaves, and it's a large spectrum
Mm.
over all the names that it has been called in the past in just a moment. And then there's a break here where you get into the infrared spectrum.
Right.
And this is the world of high energy lasers. And most of the ones that are used uh, destructively are over here. And this narrow little slit out of
Right.
the entire electromagnetic spectrum is the visible spectrum, and you have to
Okay.
expand it out.
That's all
This is
we
all an
see.
eyeball see right here.
Oh.
So there are high energy lasers that can reside in that, but because they would be visible, most of the ones that are best to penetrate the atmosphere are over in here,
Okay.
in this infrared and deeper. And then we go
Okay.
to ultraviolet and get on out here to gamma rays and stuff. So X-rays are up in here. So there's a whole spectrum that is huge. And then look at that little thing. That's all our
That's all
eyeball.
we see. Right. Oh, wow.
But there are sensors that can see these things, and
Of
that's
course.
an important part of the feedback loop. And of course, the high power microwaves, again, like the lasers, you can't actually see those. So let's take another another look at
Aha.
we have what is a laser after all? And laser stands for light amplification by stimulated emission of radiation, LASER.
Yay.
And here is just a graphical, simple diagram. There's an energy source here, and it's pumping into this gain medium. And the gain medium could be a number of things, but it's usually chosen so that it makes the light sort of march in line and become what we call collimated into a
Uh,
laser beam. And so on one side of this is a resonator where
mm-hmm.
the light will bounce between a perfect mirror where it can't escape and a near perfect mirror when it gets to the right energy levels that allows it to come out. And this
Mm.
light's not like a flashlight, it's now collimated, meaning that all the rays are lined up, marching together, and
Ah,
that's what makes it such a concentrated beam.
right.
And depending on the optics it's going through, it can have various sizes. Obviously, for anyone that's used a laser pointer, you know
Mm-hmm.
that that's an extremely tiny beam. But you know, as you scale up, you can make very, very large beams. But they share one thing in common. It's collimated energy. So the energy source is the pump. That's this thing depicted. And energy is applied to the gain medium. That's up here in this red and causes the atoms and molecules to excite.
Mm-hmm.
And if they excite, they go into if you think about the quantum mechanics of electrons, you know, orbiting protons and
Yeah.
neutrons in an element, uh, those electrons would jump up when they're excited to
Bing.
another quantum gain.
To a quantum level, right.
Yeah. And
Okay.
when they jump back down, they emit something we call photon.
Right. That
And those
principle
photons,
there of electron shedding energy is so fundamental to how so many things in the universe works. I
yes.
mean, light. I mean, there are a few other sources, but electron shedding is so important. We'll probably talk about plasma, and that's why you see it. So yeah, good one.
So that's excited atoms and molecules that
Yeah.
release the photons. When those electrons jump back to a
Right.
lower energy state, that's how they release that excited energy. So we talked about the gain medium and the resonator up there. So that's basically a laser. So let's now look at the next level of this.
Mm,
Hold on. Let's just do a little bit of
good.
basic directed energy physics terms.
Yep.
So we'll start this is probably, I mean, maybe some people haven't seen this in a while, but nothing here is more than what you would probably have learned in a high school type science course.
Yep.
So hopefully it's not too foreign and we won't spend a lot of time in equations here. But let's start with what is a Newton? Well, that's a measure of force, and
Yeah.
we use the letter N to be a force measurement. And force is equal to mass times acceleration. You know, the old equation F equals ma. So in this case, mass would be represented by this term kilograms, and acceleration would be meters per second squared. So when you
Yep.
multiply mass, kilograms times meters per second squared, that's what a Newton of force is.
Right. One
So
Newton.
one of
Right.
those is 1 Newton.
1 kilogram over 1 meter squared. Yeah. And one
One,
N. Yeah.
yeah, 1 kilogram times a meter squared, meter
Mm,
over uh, meter per second squared. Okay, so then the next term
sure.
we're going to talk about is a joule. Joule. Joule is an energy term. So now we've gone from force to energy. What is energy? Energy equals a force times a distance.
Distance. Right.
So if you're like pushing a block, for instance, let's say you want to push a block 5 feet. Well, that takes a certain amount of energy,
Yep.
and that energy is really represented by force, the amount of force you have to push on that block times the distance you want to move it. And you know, that'll take a lot of energy out of your body if you're trying to do something like that manually.
Sure.
So 1 joule is equal to 1 Newton from above, the force thing, times meter, which was the distance.
Right.
So that would be kilogram times meter per second squared times a meter. So
Right.
now we got kilograms times metered squared over second squared, which can also be represented as a Pascal times meter to the cube power,
Sure.
or it can also be this term down here below, watt
Watts.
times seconds.
Right.
So we can reverse what's a watt, which is power, and that's energy divided by time.
Yep.
So energy is a joule. So a joule divided by time would be joules over seconds.
Yep.
And we reconvert that back then to some of these other terms and say,
Yep.
well, that's a Newton meter per second times kilogram times meter squared per seconds cubed.
Yep.
So those are different ways you can look at that term. But what's important here is when you have energy divided by time to be a power, think about what happens if you make time a number less than one. So say it's 0.001.
Okay.
Well, now that makes the power that you get when you do that work, that division, very, very high
Right.
for a very short, brief period of time. That's called peak pulse power, and that peak pulse power can be gigawatts. It can be a lot of
Oh,
power,
right.
but only for briefly. But that's all you need to
But that's all you
trigger
might
the
need.
effect for high power microwaves. So high
Ooh,
power
clever.
microwave use the term power. We call them high power instead of a high energy because we're really looking for that peak pulse power that comes out of this part of the
In a
equation.
short period. Right.
Yeah. And we use power in lasers as well, but most of the thing that we want the laser to do is to accumulate energy, these joules, for a
Right.
brief period of time. And
Right.
so that's why we talk about high energy lasers and high power microwaves.
Yeah, great, good. Well, very clever. Well explained, Dan. Good. I get
Okay,
that.
so let's move on then. These are some typical laser measurements.
Oh, wow.
Irradiance is a term that's basically it's delivered laser power divided by the beam area. So your
Hmm.
beam would have some sort of a circular area equivalent. So that would be power in a given area, as in watts per meter squared.
Right, right.
That's irradiance. Think of that as the concentrated light that's being delivered in a spot.
Spot.
Yeah. Then fluence is
Fluids.
irradiance, the previous term, accumulated over a dwell time.
Yeah, yeah. Bzzz.
Yep.
Right.
So that's the density of power on the target, this term above, watts per centimeter squared, multiplied by the dwell time of power delivery. So watts per centimeter squared times seconds.
Wow.
And so the longer you dwell that energy onto the target, that power that's into the centimeter squared,
Sure.
you now, because you're multiplying by seconds, you're turning that into energy that's being accumulated in a spot, and that's called fluence.
That's fluids. Right.
So fluence is accumulated energy in a given area, in other words, joules per centimeter squared. And again, this all goes back to the previous chart, the brief mathematics on what's the relationship between these terms.
Right.
And then another term that's sometimes used to compare one laser system to another is called brightness, which is it's not like we think of, hey, my eyes are really squinting because it's very bright. No, it's a range from lasers. It's a range independent figure of
Right.
merit for a
I'm
laser.
married.
And so
Hmm.
that's power, that's watts, over a solid angle. And a solid angle is called a steradian. So
Ah,
watt per steradian. And
great.
that's not used greatly, but it allows scientists to compare one laser system
You can
against another,
compare. Right.
regardless of the ranges they're achieving.
Okay. Great.
All right, so a laser requires both inputs and it has outputs.
Yeah.
And some of those outputs are useful and some are not useful.
Right. I
And the
bet.
non-useful part is the waste heat. So you want to get the light out, that's the positive output, but waste heat represents a lack of total efficiency.
Hmm.
And you have to do something with that
Ah,
laser system or it'll melt the whole system down. So you have to
sure.
deal with the waste heat thing, which is both inside the laser and in lots of components that are connected to it.
Of course.
They come out of the energy source not being perfectly, it's not 100% efficient. We started out with lasers that had very low efficiency ratings, and we're getting up to the point where they're nearing 50%, but that still means half the energy you're putting into the laser is coming out as usable
Heat. Yeah.
laser beam, and the other
Yeah.
half. And so you can have inputs that include power, such as gas or chemical lasers.
Hmm.
Gas laser being the most common is CO2, carbon dioxide laser. Chemical lasers, such as the chemical oxygen iodine laser coil, and those produce an exothermic chemical reaction. Exothermic means, releasing heat
Yeah.
in the chemical reaction, but in the process, that's providing a pumping source into the gain medium that then gets back and forth between the near perfect or the perfect mirror and the near perfect mirror, and it
Okay.
connects to the laser beam. Optical, such as a flash lamp or a light emitting diode, can trigger smaller lasers. That's usually
Right.
what you find in like a laser pointer that you might use when you're getting ready.
Sure.
The light emitting diode is where that laser light's coming out of, and you're usually powering that by a small battery. And then electrical, you can have larger lasers where you're just adding electrons to be the energy source,
Right.
because the system is actually taking those electrons and converting them through some methodologies to become a laser of a given wavelength that you're desiring for an outcome.
And this all depends on adding energy into this gain medium by exciting electrons into higher states of orbits and then letting them decay back down again.
Exactly, and that's why it's bouncing back and forth between the perfect mirror and the near perfect mirror in order to produce that. And I'll show you some
Good.
examples. Um, let's now let's bust some myths about
Okay.
lasers.
Good.
Everybody's seen plenty of Hollywood movies,
Yeah.
and unfortunately, if you've seen those, you're getting the total wrong idea about what a laser really is.
Okay.
Typically, you cannot see weapons class laser beams with your
Hmm.
unaided eye.
Of
You may see them with the right sensor,
course.
and it's also traveling at the speed of light. Now, when you watch a beam go from the Star Trek Enterprise over to the Klingon, bird of
Yeah.
prey, it actually travels at a speed that you can tell it's moving from one ship to another. In
Sure.
actual fact, though, the speed of light, which I put it here in terms of Mach number, if you compared it to like jet fighters,
Sure. I like
F-111
it.
could go 2.5 times the speed of sound. Well, in Mach number terms, it's over Mach 1 million. And then
Right.
so you say, well, hypersonic kinetic, missiles and stuff, weapons, they can go Mach 5 to Mach 10.
5
Well, even at Mach 10, what's
million.
that? That's like way down here. So the laser can overcome and overtake about anything out there in terms of kinetic type weapons.
Hmm.
So again, it's the effects of the laser beam intersecting an obstruction or a target depends on the power, wavelength, and target material. So the laser light will couple and deposit energy at different rates depending on the type of material. If it's a perfect mirror, then it's probably not depositing much at all. Most of that's being reflected off. So you have to really think about and decide where you're going to aim that laser
Ah.
and then what wavelengths are going to couple the best and so forth. So that's why there's lots of different designs and lots of different kinds of lasers.
So if
But
you need to know what your target material chemistry is of a missile or enemy airplane or ship or whatever you're firing, it is going to help you tune the wavelength of the DE laser weapon. Is that right?
yes, and even more importantly than that, when you're actually aiming it, you're not, let's say you're trying to hit a particular, let's say it's a drone.
Yeah.
Somebody's got a drone, it's an
Yeah.
armed drone, it's got a weapon they're going to try to drop on you. Let's say you want to take that out before it comes over what you're protecting.
Hmm.
Um, you don't just treat that drone as a target because the laser beam is very precise. You need to also have figured out well in advance what's the weakest point to put your laser on that will take that out in the quickest amount of time. And so that comes down
Ah.
to where's the structural connection between the wings or the rotor blades or
Yeah.
what kind of a drone it is. And so you're looking to aim it very precisely. And of course, the optics of the laser system, and if it's a laser in the infrared wavelength, that's an infrared optic set, but you're also using that as a telescope because you're seeing directly magnified like a telescope coming back the other way, looking at your target very precisely. So you want
Sure.
to put your crosshairs on the known endpoint. Now we're automating that with a lot of AI now, so that the that can all be loaded into the algorithms, and a laser can aim itself because it can do a target recognition, and then it
Fantastic.
has in its data banks, okay, well, here's the best place to take that target out, and then it
But
just
I'm putting my science fiction brain on here. Tell me I'm wrong, but this is a good question. So instead of it being just a beam of light with energy and heat, because it's energy in the form of, say electrons, you want to call it, or photons, the same thing really. You could you target, say, a motor and overload an electrical system with more electrons? Rather than burning a hole in something, could you use the energy of the beam to affect electronics, for example?
yeah, not so much because electronics are usually housed below structure and not necessarily.
Behind, yeah.
Yeah, but you could do that. Well, when we get to high power microwave, that's an excellent question because
Ah,
those wavelengths of energy do exactly that. And
I
they don't
wondered.
need to burn a hole through anything to get there. They go in through the front door if there's an antenna that's connected to the thing, like a
Right.
radar in the front of an airplane, or if it can go through what's called the back door seams and cracks, and can get in that way and ride down, internal
And then
wavelength.
it goes in and affects
Yeah.
the actual physics of the system. Oh, I like I'm
Yeah, gets into
oh
the actual circuits, burns
right,
things out, trips it
right.
offline. Sometimes it might be depending on the amount of power you put into it, it might be a temporal effect where it's going to be only for a period of time, and then it
Yeah.
might reset itself, or the computer might be able to be down booted and then booted back up, and it might come up. But that might give you enough to
Yeah.
escape through undetected with whatever system you're trying to basically defend. So. The
I
last
like
thing to
it.
say on it is it's not like phaser bullets like you've seen in Star Trek.
Well,
There are no kinetic effects from a laser.
right.
None. It's all thermal.
Hmm. Hmm. Hmm.
Okay, so let's move on then. Energy and power. We've got the thing we had earlier here, just the cartoon depiction of a laser system.
Yeah.
And energy we know is measured in joules, power is in watts. And so laser power typically measured in watts, which is joules per second, as we saw in that earlier chart.
Sure.
But let's do some comparisons, things that incandescent light bulbs,
Right.
although they're not around as greatly as they used to be, but let's say a 75-watt light that maybe is powering up your kitchen
Yep.
produces usable light. So we're 75 watts, use that as sort of okay, that's how many
Mhm.
watts that is. And then if you got to ride a stationary bicycle, an average adult can generate 125 to 200.
Oh,
If you're a world-class Tour de France bicycle rider, you're probably up in the 4 to 500 watt range.
sure. Wow.
But this is what an average adult can do.
Hmm.
And then if you translate watts into horsepower, 1 horsepower, like for car engines, let's say, is
Hmm.
roughly equal to 750 watts. And then I've given an example here of a kind of an extreme dragster that you could buy as a commercial vehicle, a Dodge Demon.
Yep.
That engine develops 630,000 watts, kilowatt.
Whoa. Right.
You burn a
Sure.
lot of rubber off with that in the drag strip.
Sure.
You go and look at the Swedish design Koenigsegg.
Yep. We know it.
Koenigsegg Regera generates with because it's a hybrid electric and very good internal combustion engine.
Sure.
1.1 megawatts, million watts out
That's
of
a
that
car. Yeah.
the car. So
Wow.
uh, laser power over an area is called a radiance, as we talked about earlier. and
Sure.
that's in watts per square centimeter. So that's just some things to kind of gauge what is all this power and how do I relate it to common life?
Yes.
Although I can't relate to Koenigsegg Regera because those are
No.
hyper-millionaire like supercars, but it's
Yeah.
fun to watch them on TV. All
Me too.
right. So now let's do another common example. A lot of people have either used themselves, or maybe they got a brother or an uncle or a friend that's used an oxyacetylene cutting torch.
Yep.
And it has about a 1 centimeter squared flame size. That's this little part right here
Hmm.
coming out the end of the gas reaction. And whoops, sorry, what do we use it for? Well, it is used to cut through things. It melts them
Right.
by the heat. And it produces about 1,000 watts per square centimeter. So that's its irradiance.
Yep.
And that's a coupled heat, so it doesn't include heat lost and flame splash. You see a lot of this. But that's the coupled heat that's represented at the tip of that.
Sure.
Now, let's say that you have a 1,000 watt laser system that has a 1 centimeter squared beam size.
Hmm.
Okay, so if we take watts per centimeter squared, that's a radiance. So we actually get 1,000 watts per centimeter squared here. We get
Oh,
a
wow.
thousand watts per centimeter squared. So the irradiance of both the laser and the cutting torch are the same.
Right.
That's coupled heat, doesn't include any reflection, heat loss, or material effects. And the materials can spall and bubble up and cause some losses. And it also does not take into effect transmission.
Right.
So as a laser goes through the atmosphere,
Right.
it encounters random dust particles. It encounters other things like turbulence of the heat rising up from the earth.
Hmm.
And you have to compensate for all those things inside the laser system to the best you can, but it's never perfect. So, if you're trying to go take a laser through a thunderstorm, the likelihood is that will all be absorbed in the thunderstorm instead of penetrating through it. Little bit
Yeah.
for other wavelengths for the high power microwave systems. So we'll see that that's kind of they're partners in the same thing, that is doing directed energy as a weapon.
Ooh.
So, and then there's diffraction, which is spreading of the beam,
Right.
because no aperture is perfect. And at the corners of, say, your lens that it's emerging from, there will be some amount of diffraction, which is slight spreading of the beam, but
Right.
you attempt to reach what's called diffraction limited in the design of your optics for the interface of the laser to the atmosphere. And
Right.
when you do that, diffraction limited minimizes that to the lowest you can possibly ever get it to. So anyway, if you use these two systems, an oxyacetylene blowtorch or a 1,000 watt laser,
Yep.
as cutters, the effect would be roughly the same. And that's why there are widespread uses of fiber lasers now
Yeah.
in the manufacturing industries.
Sure.
Use
I
them
have one.
because they're a little bit more efficient cutting torch, and you don't have to have all the gaseous sources to
Yeah. Good.
you just plug it into your grid power, and away you go.
Hmm.
Okay.
Yeah. Again, science fiction head, physics head on here. I always wonder. I have a plasma cutter and an oxyacetylene and a laser. I always think it's not really melting. It's more disrupting. I always think it's more of a disruption beam. It's splitting the material more into its basic elements, and that produces heat and light. But I don't know. That's how I always think when I use my laser.
Yeah. Well, however you want to think of it, it ends up in the end burning a hole through
It
something.
still burns a hole. Yeah.
Yeah.
Right.
All right, let's go on then to these are just a few solid state lasers. Solid state meaning they don't depend on gas or
Okay.
chemical. You can power these with electricity, and small scale ones like we talked about the laser pointer.
Hmm.
That'd be a thin disk laser. That's what's in the end of that thing that's putting out laser light. That's
Hmm.
very small and manageable. Obviously, it's not something you're ever going to burn through. You still don't want to look directly into it though, because it
Hmm.
can damage your retina. But The other type that's common is electro-optically pumped, diode pumped, which converts DC power to light.
Oh,
Wide commercial use for that in manufacturing and medicine. But in the manufacturing, it's kind of migrated from this to this now. The bottom one here is fiber lasers.
yeah,
So the fiber is, if you're familiar with what a fiber optic is, a
sure,
fiber optic would be this outer part, the tube with the material inside that light, and I'm showing how it can be bent and light will travel around through and come out the end. We've probably all seen those fiber optic wands and stuff that, at circuses or fairs,
sure.
and you turn it on and light comes out the ends no matter how you wave it
Yeah, yeah.
around.
Internal
Very
reflection. Yeah,
flexible. Yeah.
right.
Well, what's different about a fiber laser is there's both a cladding on the inside, which is a silica cladding, and then there's a single mode core in the middle of it that's
Ooh.
manufactured in, and that's your doped material. That has
Hmm.
the properties of the actual gain medium, and depending on how you dope this is going to determine uh, what wavelength of light comes out. For
Mm.
instance, in let's say that you have a fiber optic connection to the internet, which is
Hmm.
high speed, equally fast for
Do.
both uploads and downloads.
Sure.
Those are usually transmitted at an eye safe level of 1.54 micron.
Oh,
And at that wavelength, it's considered eye safe, so it's suitable to use. And then you can, of course, embed data into that light stream on the
sure.
laser in the fiber optic, and you can get a lot of data in there compared to what you can on a copper wire for, say, a normal cable.
Yep.
So similar here, you could actually use a fiber optic and that type of laser. The way it bounces back and forth is this fiber is not straight when it's in the laser system.
Ah,
It's actually coiled
ah,
around at a certain bend radius, and now as it bounces back and forth, going through the gain medium, and now these outer claddings, no matter this, so we're spherical here, so
hmm.
the outer cladding in all directions keeps bouncing it back to the single core mode, the single mode core, and that is now producing um, excitation of electrons in a very specific frequency, which will determine what the output coming
Hmm.
out the end here of your laser light will be. And
Well,
that one will couple to your optics system.
and that's so literally the. Do you think the actual doped core goes right through the whole of the fiber laser, right to its output, or is only a
Yeah.
short section of it with the core, and then
No,
just a fiber?
it goes through the entire core.
Oh, right.
So the entire length of fiber that you've now coiled up
Right.
in order to have the right amount of time for it to bounce around before it comes out. So think of the resonator, the near perfect, and the
Yeah.
perfect. So the perfect mirror is along that path because it can't get out yet. And the near perfect mirror is when it gets to the very end of the fiber coil, and that gets mated to your output optics, which
Your
again
lens. Yeah.
have to be tuned to the wavelength. Your coatings and stuff have to be tuned to the
Of course.
wavelength you're producing. And so there's an outer cladding around this whole fiber
Mm.
that's polymer. So the light can't escape. It's trapped to bounce between this inner silicon coating and come across this core
Mm.
and exciting electrons out of that core, which then are lining up and now coming out as a collimated, all in line. They're not going out in all kinds of different directions like a flashlight. They're coming in a beam that's all lined up. Everything's marching along in a linear line.
I love it. I want one.
Yeah, well, solid state lasers and fiber lasers were not considered to be useful when I first took over the program
Ah,
at the Air Force Research Lab. But I looked at the chemical lasers they were using for like the airborne laser, which
that's
was
right.
747 modified. And, when you think of that from a logistics standpoint, the deadly chemicals that have to be hauled and kept to refuel wherever you're going to land and refuel your laser, that's a problem. The
Mm,
chemicals on board the airplane, should they, get a leak or something,
right.
that's a problem.
Problem.
And if the airplane were to crash, it'd probably kill everybody within a 5 mile radius of the crash point because of the deadly nature of those chemicals. So I
Eh,
thought, warfighters are not going to want the logistics headaches of taking a chemical laser into battle.
right.
And of course, a big 747 is not a very stealthy aircraft, and so it's going to be a target for any kind of missiles or fighters.
Sure.
So I predicted that that was going to be good only for the research value of proving
Mm,
it could shoot down an ICBM during the boost phase.
mm,
It did prove that,
good.
and it was quite good. But I started working on fiber lasers, and the other laser scientists are saying, "No, you're an idiot," because Southampton University had predicted that the maximum output of a fiber laser was this tiny amount that wasn't really useful.
Right.
But I found a small business, and they were really into this, and we started talking about how we could
Yeah.
do multiple loops of this, with one feeding the next stage, feeding the
Ah,
next
stages. Right.
staged fiber lasers.
Ooh.
And we were able to demonstrate after about 6 months of work, we got that maximum out of one tiny fiber was now two orders of magnitude, so over a
Right.
hundred times what the published theoretical maximum was. And
Duh.
once we had that proved, and we had other laser physicists come, scientists come and look at that, they started to say, oh, well, maybe this is not so unuseful. And now, at this point, some 25 years later, we're at the point where um, actually every defense contractor in the U.S.
Yeah.
has gone to this fiber lasers, and we're not talking about a single fiber. We're talking about banks of fibers that can all
Uh,
be bundled together to
right.
create a much larger total beam.
Right.
And it has a lot of fail redundancy, because you
Yeah.
could lose several of those channels and still have a very useful laser.
I get it. Oh, cool. Very good. Can I ask you a really silly question?
Yeah.
Everybody wants to answer this. When you shine a laser from a laser pointer, why do you only see if it's, say, a red laser? Why do you only see it when it hits the wall or you play with the cat? Why can't you see the laser in midair?
Oh, that's a good question. Yeah, it's because the specific wavelength isn't readily concentrated enough for us to detect it. I guess if you had perfect eyesight, or you put on some
Yeah.
goggles of some type, you might be able to see it in midair, because it is a visible wavelength, but it
Oh,
becomes
yeah. Obviously, in theater and in rock roll concerts, you can see laser beams with smoke. But I mean, why can't you shoot a laser and it stops?
oh yeah,
Yeah.
yeah, it doesn't do that. It goes
No.
until it impacts something. Yeah.
Right.
So yeah, and you can actually see if the laser's large enough and in the right wavelengths.
Yeah.
Show lasers, you can see them even without smoke. They just, you can actually visually see the beam as
Oh,
it goes up and away. But a
right.
laser pointer is a tiny, tiny beam, and really, it's most effective is if you have a reflective projector screen,
Sure.
and now, just like the light from the projector that's showing the pictures on the screen, it hits that screen as well dispersed and reflected back. It doesn't come back totally collimated as it reflects off of it, and it's detectable. In fact, it doesn't even look like a collimated speck. It has kind of an edgy look about it when you see it on the screen.
And as you look, yeah. Okay, good. Thank you, Dan.
All right, so let's go a little bit more myth busting.
Good.
Laser effect. Got to bust these myths, because it's hard for when I teach warfighters, they've seen too many Hollywood movies. So they think about Independence Day, where the giant aliens UFO spaceship thing sends
Yeah.
down a beam and just literally vertically collapses an entire uh, superstructure, a big circular multi-story building.
That's
Uh,
right. In LA.
Yeah. So lasers do not cause instantaneous spectacular destruction.
Ooh.
See this thing not only in Independence Day, but in Star Trek, like Wrath of Khan or some of those kind of movies. The beam, when it hits the ship, they always have kinetic effects. So things blow in like a bomb went off, and people go flying through the air, over the rails, and over their chairs,
Yeah.
into the floor. That's not how it works. There are
Oh.
no such now. If it actually burned a hole through the ship, you might see something going the other way where the vacuum of space is sucking everybody and everything out of the ship. But it's not the laser causing that, instantaneous spectacular destruction. And as we talked about before, the laser effects are integrated over time.
Right.
Remember, it's watts times seconds.
Hmm.
And that's what gets you your irradiance, which ultimately is effectively fluence, accumulated heat.
Right.
Now, that's times required, but that may be a very short amount of time, maybe just a few seconds to achieve that burn through effect, but it still takes a little bit of time to do
Mm.
the effect. However, if you shoot a missile and a missile's traveling at Mach 5 and you shoot a laser which is at Mach 1 million, which one's going to get there first?
Yeah.
So
Yeah.
it's for most applications, the laser is virtually instantaneous because it's getting there so quickly.
Right.
But you have to hold it on that spot for a short amount of time for the accumulated laser energy
Energy.
fluence to have its effect on the material.
Hmm.
So, and lasers do not directly move people or other objects by photo momentum. If you think of the
Right.
Iron
Yeah.
Man movies, Iron Man flexes his wrist down and a beam fires out and it hits somebody in the chest and they double up and go through a brick wall. That doesn't happen with photo momentum. While
No.
photons do have momentum out in space, and that's why you can actually use a solar cell and use
Yeah.
photo momentum of the light coming from the sun, actually
Hmm.
propel a vehicle, and you have acceleration that just continues over long periods of time. So you can actually get up to some incredible speeds with a
Hmm.
solar cell.
Hmm.
But in terms of photo momentum, like is shown in Hollywood, no, that's not happening with lasers.
Mm. Okay.
And of course, as we mentioned earlier, lasers don't affect all materials in exactly the same way.
Right. Right. Exactly.
Okay, so let's sort of switch gears. Unless is there anything else you wanted to discuss about lasers?
Well, well, I suppose we'll probably go on to this one enormous aspect of laser or directed energy weapons is power supply. I mean, all this required power supplies must have become very small and dense and powerful over the years. Because at one
Yes.
time it would have been a lot of power to make these, but maybe today there are compact ways of delivering energy in short blasts.
Yeah, well, as I mentioned briefly earlier that yes, indeed, the um, the laser energy that's being produced now.
Yeah.
When we started out with fiber lasers in the lab, like I said, back in the year 2002,
Hmm.
we were working with wall plug efficiency. That's meaning
Yeah.
from the electrical current
Beep.
out of the wall to the laser was 15%, which was
Oh,
a leap over the slab lasers and thin disk lasers, which are only 5%.
oh,
So
okay.
a lot of lost energy in those, but 15%. But now because we've really mastered all the elements that are in that system
Right.
and designed them in such a ways that we're getting maximum efficiency at each component level.
Right.
We're now up around 49%, and we
Mm,
may pass that into the better than 50% pretty soon. And so the various sub-industries that work on supplying the components
right.
that go into a laser system are becoming, they're inventing new ways of making electrical components, and the fibers have become like they're no longer chemically doped. They're actually doped in a very precise, like
Yeah.
molecule by molecule way to make them very, very no impurities inside the fiber and so forth. And so there's a lot of improvements across the board that are helping this. But yes, you need even now you need at least twice as much input energy
Right.
than you do to get whatever output that you're desiring to put on target.
Even if they're
And you also
50%.
have to,
Right.
yeah,
Right.
and then you have to deal with not only the 50% uh, we got laser power coming out, but the 50% heat that you now got to remove from your laser system, or it'll melt it down just from the waste heat. So you have to have
Right.
some very good waste heat management systems as a part of it. So it's
Okay.
not quite as simple and easy to do as it might sound, but it's, the fact that it's Mach a million leaving the system is a good advantage. And the fact that it can do some things that are complementary to, and maybe in many cases better than kinetic weapons. So that's
Yeah.
why there's such a pursuit over it, and it will continue to get better. I can't say the exact power levels, but it would shock you where
Okay.
we've gotten to in fiber lasers now.
Okay. Right. Good.
All right, so high power microwave. So this
Yeah.
is that other end of the spectrum. Like we talked about earlier, you had the part of the spectrum where there's the high power microwave, and it's really a collection of frequencies there. Radio frequency, microwave portions, millimeter wave portions. And because there's so many different terms that have been used in the past, and those
Right.
alternative terms are talked about here.
Yeah. I see them.
Down on the bottom, this death ray, as you'd mentioned, that's a term that was coined by people for the thing that uh, Nikola Tesla had done.
Yep.
He was the first to actually project electromagnetic energy,
Hmm.
and he was quite ahead of his time.
Mm.
I think he's more of a genius than Einstein was because
Mm.
he would design things in his head and he would engineer them so detailed in his brain that when he built an actual physical thing, he never had to modify it. It
It
worked
worked.
because he did all of the iterations and figured out in his brain before he built it what he needed to change in his design in his brain. It's like astounding that anybody does that.
Fantastic.
But anyway, so we're at the high power electromagnetics, high
Yeah.
power radio frequency,
Yeah.
electromagnetic pulse bomb,
Yeah.
non-nuclear EMP,
Hmm.
radio frequency weapon,
Hmm.
intentional electromagnetic interference, high
Okay.
energy radio frequency or HERF, ray gun, death ray.
All the
Since
same.
there's so many terms out there, in the US, we've standardized to say anything that was used to be called any of these things we're going to have one term. We're going to call it high power microwave, even though not all of it's in the microwave band.
Ooh.
And of course, we think of microwave like our microwave ovens, right?
Yeah. That's what I do.
Well, so that's about 2.4 gigahertz.
Hmm.
Our microwave weapons are nowhere near that spectrum because that happens to be the spectrum that excites water molecules in your
Right.
food and makes them vibrate more. It gives them energy, which then turns into heating your food, as long as it's a food that's got an adequate amount of water molecules in it.
Yeah.
But high power microwave weapons can be much higher and out of that, like a high power microwave weapon um, for um, an anti-personnel application would be up in the almost 100 um, as far as on the spectrum, not 2.4
Okay.
gigahertz, but 100 gigahertz. And that would be a type of weapon that doesn't, it's not like putting a cat in a microwave. And unfortunately, a lot of our warfighters first thought that. So we really have to help them understand that no, it's a brief pulse that deposits energy in the skin just a 64th of an inch from the surface, but
Ah.
it affects every nerve cell that's right there living in that part of the skin all over the body. So your body feels like psychologically that your entire body just caught fire.
Ooh.
You're holding a weapon, you tend to throw it away because your hands are hot and you think the weapon's doing it. The weapon.
Yeah.
but it's really momentary. There's no permanent effect. It doesn't even give you skin, it doesn't give you a sunburn or anything. But the psychological effect is tremendous. So
Ooh.
again, these systems can do things that are um, kind of unimaginable. It does seem like science fiction.
Yeah, horrible, but
So
effective. Yeah.
yeah, very effective. And we actually, I've been in the beam because I was in charge of
Did
it.
you have it tested on you?
Oh yeah, and
Ooh,
it hurts really.
it hurts.
And you physically can't stay in the beam. And the
Ooh.
beam is concentrated within, if you had two people standing side by side, you could limit it to just those two people.
Oh,
And
wow.
it's kind of a tourist or terrorist filter because the
I
tourists are
bet.
going to run away and the terrorists are going to drop their weapons and skedaddle. But
Perfect.
yeah, it's not been used because the warfighters thought of it as like, well, I'm not going to be the first guy to be on CNN that basically, roasted cats, killed cats in a microwave. Think of the cruelty of that, and because the word microwave for everybody's mind is their
Right,
mic,
it's an oven.
and
Right.
it's not anywhere near the same frequencies. But
Okay.
sideshow there. So let's talk a little bit about how you get an electromagnetic wave. First of
Yeah.
all, it's initiated by accelerating electrons, not
Ah.
just not just having a stream of electrons, but you have to have something that accelerates them. So they're now increasing in speed. The electrons are traveling faster and faster.
Hmm.
And when they do, the result, and I've shown it here best I can on a two-dimensional screen. Look, this plane is
Hmm.
going up and down on the screen, and this other plane is going, sideways to that,
Yep.
90 degrees out of plane.
Yep.
And there are two fields that are also 90 degrees orthogonal to each other.
Hmm.
One is the E field, the electric field, and it's going in this one that goes up and down in the screen. That field is tracing a wave that goes up and then
Yeah.
down at the bottom and back
Right.
up, and that's called the E field. And then marching along with it, 90 degrees out of plane, so it's now going this way,
Mm-hmm.
is the magnetic field or the B field,
Ooh.
and it's waving like this
Mm-hmm.
along this plate. And so those two fields, electric and magnetic, are moving along in those two different 90 degrees out of phase planes of polarization. And then ultimately, the electrons are accelerating in this direction. So that's the direction of transmission.
Yeah, we had this guest who talked about linear motors, and he had this great model where he took a normal stator and unrolled it and made a river that would flow along it. So, I mean, something
Excellent.
similar.
Yeah, excellent.
Yeah.
All right. So then here's the components of a typical high power microwave system.
Okay.
You have to have prime power. That might be your wall plug, it might be a generator, but you need electrical power because we're going to deal with the electrically initiated high power microwaves because that's more common now.
Okay.
You can actually create this with some very clever explosive stuff, but that's a one-time use, and that was back in the early days, the way that they could create a wave like that.
That was
But
for EMP.
EMP type bombs, yeah.
Right. I see. I know. Right.
Um, so radio frequency and microwave generation, that's out here in this part. There has to be an antenna to get it out of the system, and then you got to integrate all the components into a system. And again, it's not perfectly efficient, so you have not only you have to have more prime power to compensate for the inefficiencies of all these components,
Right.
and the overall efficiency is, let's give them the benefit of the doubt and call that 50% at this point in time.
Okay.
So you got to have double the power of what you're trying to put out.
Right.
And then you've got to deal with the unequal amount of waste heat from all these components. So you have to have heat extraction and heat dissipation things. So when you
Hmm.
create one of these, you have to in systems integration, you have to figure all those things out, and your systems engineering gets quite complex, just as it does for lasers.
Right.
But this pulse power source is the key. We talked briefly earlier with the mathematics of it. If you take power, which is joules divided by seconds, so visualize J over S here,
Yeah.
and you make seconds be not a large number like 2 or 3 or something, so it makes that top number smaller, but you make it 0.000001 second.
Mm-hmm.
Now, the ultimate power that you get out of that amount of joules, the energy, is enormous during that single pulse. So that's a peak pulse power. The peak of your pulse on whatever the frequency of your wave is, that's what really delivers the knockout blow. So peak pulse power. So we call it high power microwave because we're trying to achieve peak pulse power. So here's, again, radio frequency microwave or millimeter wave. An HPM system can be any of those depending on what system you're trying to disable or at least temporarily knock offline.
Right.
And so that target can be, like I said, temporal or temporary effects, or they can be persistent effects where they're going to have to replace a circuit board or something before they can get that
Right.
working.
Right.
And again, the idea is maybe give your other strike force enough time to get past whatever system that is and get to their targets, even if they can repair it and maybe have it up to go later.
Right.
It's
Or
harder
reboot it.
to
Right.
target effects assessments because often you're talking about something in a building and you can't, nothing blew up and the building didn't come apart.
Yeah.
You can usually see if it goes offline by other detection means.
Sure.
So there's a direct front door, which means if the thing you're targeting has an antenna,
Yep.
target that antenna and get it to go in the front door because that antenna is connected through coax cables and waveguides directly to the circuits.
Mm-hmm.
So that's called in band, and you can even be out of band a bit and still have an effect. So direct front door. Then there's an indirect back door where you end up going through apertures and cracks and seams and unprotected cables and still get some energy in here that reaches the circuit boards. And if you're powerful enough and close enough, you can achieve the same effects that this does, even through the back door.
Aha.
So kind of interesting because you can't do that with the laser. Of course,
Right.
that's strictly a front door thing and you're coupling to a specific aim point. Here, you're going through the entire architecture of the building, the cabling, the tunneling, and have a chance to get power to come into the circuits of interest because this electromagnetic wave of radio, microwave, or millimeter wave energy can penetrate building walls. It
Right.
can penetrate a lot of things. It's not in the wavelengths like the laser, which doesn't go through materials. It has to interface with them. And then those photons start converting back into a different form as they impact that surface because it's not transparent to them.
Yeah. Yeah. In HMP, what would be the kind of maximum range to affect either in band or indirect?
Yeah, well, there's the HPM is not a collimated wave.
Right.
And you can get a beam that's fairly tight. But if I say a laser weapon is like having a sniper rifle
Okay.
with a blowtorch, and the blowtorch can go like a oxyacetylene blowtorch
Yeah.
at the speed of light to a long distance away, but in a very, very tight beam.
Yeah.
I can say that's a blowtorch on a sniper rifle as a laser weapon.
Okay.
But for a microwave, it's more like a shotgun blast of directed energy. Because that wave is going to, even no matter how you design your antenna,
Yeah.
it won't stay perfectly collimated. You can do phased array stuff to help
Right.
shape the beam and aim the beam, but it's still it's going to dissipate over 1 over r squared. And so it is a shorter range weapon, but it has, for instance, if you have an HPM weapon and you have some of these said drones coming at you, and they decide to bring a whole swarm of them
Yeah.
because they want to defeat your laser. So because your laser's got to then, kill one, then move and
Yeah.
one on another, kill another in sequence. The HPM can blast out a large enough beam
Yeah.
cell that suddenly all of the drones in the swarm fall to the ground at the same time because you fried their internal circuits.
Wow. But can you, I'm again, science fiction terms, can you imagine an HPM weapon airburst or from an aerial platform that would be maybe a city killer?
Well, we in fact found that out the hard way in 19, let's see, what was it, about 1962, I think. Uh,
Honolulu.
yeah, they
Yeah.
decided to test an airburst, not in the air, but in space.
Yeah.
So it was above the ionosphere. Didn't realize that the gamma rays that come out of that bomb burst in space would hit the ionosphere
Yep.
and start knocking electrons out of orbit that then will, the ionosphere, like think of a sphere surrounding the Earth,
Hmm.
it becomes like a uh, concave focusing lens.
Uh,
And that energy then comes down as an HPM kind of unintended weapon, and
uh,
it has very broadband applications where uh, when they did that, called Starfish Prime,
yep.
it actually, from a long ways away, it took out the telecom systems in Honolulu and caused power failures in Hawaii. And also up in Alaska, it knocked some microwave towers offline in the Aleutian Islands. So
Oh,
uh,
from the start, from that same Starfish Prime
Starfish Prime.
burst.
And that's where
Yeah.
we really learned about electromagnetic pulse and how
Yeah.
destructive that can be. So that's one to worry about because, you wouldn't want to have that if it was set off as a in-space airburst above your country. Probably
Right.
knock the entire grid out. So not a good day.
And often seen in war planning, EMP pulse bursts would be a precursor for an attack because it would help, it would assist an enemy in taking out your communication and power grid system before missiles came in. So it'd be very bad. I always worry when the lights go out. I look
Yep.
up in the sky.
Well, yeah, it would be like going back to the 1800s, and
It
we
would.
wouldn't have the internet, we wouldn't have TV, we wouldn't have telephones. We would just be back like the Amish live today. They're
The
probably
Stone
the ones
Age.
that will
Yeah, yeah,
survive it the
that's what they
best.
say. Yeah.
Yeah. Anyway,
Okay.
so that's how that works. So
Right.
that's in those bands in the electromagnetic spectrum, radio frequency, microwave, and millimeter wave. And you choose the frequency depending on what you're trying to take out. And these are useful
Yeah.
for disabling or exploding out in front of you where it's not going to be a blast danger when you have implanted in the ground these improvised explosive devices. So
Ah.
that's become a really good use for them during the global war on terror. And for other things like buildings and systems and radars and so forth. So think of it like electronic warfare on steroids.
Oh, you can set off, say, a device that is micro-controlled by frying it, by triggering it.
Yeah,
Is
by
that
coupling it through the back door.
coupling it? That's a good
Yeah.
word, right? Coupling it. Okay. Oh, great. Oh, I've learned so much today, Dan. Dan, thank you very much.
Yeah.
Ah,
So just one
keep
last
going.
thing. We'll
Yeah.
say I think this is the last chart I built for
Okay.
you.
Sure.
So an HPM antenna, as you can see by the picture there, this red stuff would be all the stuff that's coming out of that antenna, and it's going from left to right on your screen. And then what's going behind the source, which here is here at the center, that's your antenna source.
Yeah.
You get some amount of back lobes and side lobes, and you got a
Yeah.
first upper side lobe and a first lower side lobe, and all of this stuff is not useful unless it's in this. And so these are some of the losses that cause an overall inefficiency. And also, you got to be careful because you don't want this stuff to fry your nearby, friendly stuff. So
That
you
could
have
be
to,
in your territory,
yeah.
whereas, yeah, right, I get it.
So the gain is the ratio of energy in the main lobe, that's this part,
Yeah,
versus the energy that's in this perfect pattern.
yeah,
Perfect pattern were to give all of it here, how much of this energy is actually in the front lobe, and that's your gain, and that won't be 100%.
right.
And then directivity is the maximum gain compared to the average gain in all directions. So your directivity is how much is going in this way,
Ooh,
how much the maximum gain is going that way. So antenna designs are, there's non-phased array designs, but phased array is becoming the more accurate way to do this, where you have just like phased array radars for aircraft,
sure.
have little transmitters that you can change in the circuitry in the
Lots of
background,
them.
phase
Yeah.
and cause the beam to then, because of the phase mismatch, you shape a beam, and you can shape multiple beams in several directions. But anyway, you're trying to maximize the energy that's in the main lobe while you minimize the side and back lobe energy.
I think, yeah, I think we've seen some of those in Britain.
Yeah. So
Uh,
I'm going to stop sharing now. We'll go back to our normal screen.
sure. Oh, you covered a lot, and you've actually opened my eyes to something that I've talked about a lot on my channel about a system called Cobra Mist. But I'm not going to go into that because I don't want to touch on anything classified. But what I'd like to talk about is deflected mirrors, because one of the problems, I believe, in shining lasers through our atmosphere, less not so in space, is the wiggle and twinkle of our atmosphere, by heat energy and refraction. So here in the astronomy community, we use bendy mirrors and guide stars to take the twinkle out of starlight as it passes through our atmosphere. But I heard that pretty well came from laser technology. Were you ever involved in bendy mirrors?
I was. We have in the Air Force Research Laboratory a special facility. It's kind of the southern end of the Kirtland Air Force Base, which blends into the
Right,
White Sands Missile Range. The White
right.
Sands Missile Range is under the Army's control,
Mm,
and then Kirtland Air Force Base is under the Air Force control. But that Kirtland Air Force Base has Space Directorate and for technology for space,
right.
and we have the high energy laser and another department for high power microwave. And when I was in charge at the headquarters back at Wright-Patterson in Ohio,
Ooh,
I would come out to Kirtland to meet with my laser expert, and be a colonel running that and another colonel running high power microwave.
great.
In addition to that, the Starfire Optical Observatory
That's right.
is a telescope facility that's located just beyond the Kirtland Air Force Base range area. There's a road that takes you down, and kind of at the very top of the White Sands Missile Range.
Oh,
And yeah, it's really fascinating because I sent you the name of the scientist that worked out there that had um, he actually came up with the first uh, implementation of a sodium wavelength laser, which most people said, like they told me, fiber lasers going nowhere. And now look, well, they told
right.
him that was impossible to do. You couldn't do it. And
Bzzz.
he figured it out.
Right,
And up at the top of the atmosphere is a sodium layer, and
right.
that he found a laser that could couple with that and excite it so it could actually act as a guide star. So now
Exactly.
you have almost 100% of the atmosphere between you and it, where heat waves and turbulence and all that is making the stars twinkle. So he used the guide star, and at the time there was no massively parallel processing computers. So he
Mm,
built one, and it took up an entire room. And he integrated lots of regular computer boards
Oh,
into his own massively parallel network that could process at 1,000 frames a second. So, using a special optical device in the telescope, so that the telescope works both ways. You can beam energy out, you can see
yeah.
things with the laser systems. So in the laser, which is not in the telescope but beside the telescope, and co-align to basically do adaptive optics along the line of sight of the telescope. He figured all that out, and brilliant man. And so I got to go out there and observe it before it was anywhere else. And then, of course, it has migrated to most astronomical observatories all over the Earth, and you can build a much larger a telescope on the ground than what you can put into space.
Yeah, before adaptive optics, we'd basically, through clever telescopes and mirrors and things, lenses and mirrors, we'd built the maximum that we could possibly build because we were running into twinkle problems. It was but today, Earth-based observatories can be as good as space-based ones because you can take the twinkle out.
You can, and it's amazing
It is.
And so, I mean, when you first watch it, like the system that you turn on to get that is called adaptive optics.
Right.
And once you turn it on, and it's literally, it's kind of like if you've ever used Bose noise canceling or any other noise
It's the same, right?
Same thing, but now not sound waves, but light waves.
Boop,
And it's
boop.
figuring out all of the distortions, and then the bendable parts of the mirrors, like little piezoelectric things that take a slightly deformable mirror,
Yep.
and you're able to, at 1,000 frames a second, 1,000 times a second,
Oh, right.
you're distorting the mirror so that the light's coming out of the telescope distorted, but it's being reassembled correctly up above. If you're firing a laser weapon, that'd be target in the loop adaptive optics. If you're just passively visualizing things in space, you use the active side being this guide star with a yellow looking laser that's tuned to the sodium. Sodium. That's telling you what all the corrections are. And now you have a deformable mirror in your telescope that's taking all that out, and ultimately what you're receiving from light coming down, you take the full twinkle out of the stars. It is astonishing.
But you touched on, but I didn't quite get. So what's the opposite? How do when you're firing a laser through twinkly atmosphere, what are you doing differently to telescopes?
Well, first of all, your laser itself is hitting the target. And the target becomes
and wiggling.
Yeah. And so you have a sensor, just like they do for the telescopes, that reads that and then bends the mirrors in the optical path to make
straighten it out.
And so you have a beam that would be speckly and distributed all around because of the atmosphere. But when you turn on adaptive optics, and that's called target in the loop.
Thank you.
Reflecting laser energy off the target instead of highlighting a guide star on the sodium layer like you do for terrestrial.
I get it. Oh, that's
It's brilliant, and it works. And all of our current systems by the various defense manufacturers are using that technology and perfecting it, all the time with greater and greater efficiency to it. They may be well up over 1,000 times a second with their correction factors now, but
sure.
That was the limit before we had massively parallel processing supercomputers. Now we have stuff that, can be the size of my laptop I'm using now that can do that kind of processing. But
interesting.
Yeah, it was a room full of just off-the-shelf computers back in the late 90s.
And little actuators bending bendy mirrors.
Yep. It's been very, very sophisticated, this many years later.
Well, Dan, thank you. We've covered a lot and only scratched the surface, which is the nature of education. There's a lot more to say. There's a lot more to learn. But viewers, you have got a real treat from what you've seen today. There's a lot of stuff in that you've just listened to. Well done if you've got to this point. And thank you, Dan. It's absolutely fascinating. I have a million more questions. Please come back. It's always a pleasure to speak to you.
Well, thank you for the opportunity. I'm glad to help you and your viewers kind of understand this a little better. We tread very carefully not to disclose anything that would be classified or sensitive. This was just strictly a presentation like you did if you went to maybe a bachelor degree kind of college course on how do lasers work, how do high power microwaves work. So I tried to keep it to that level so we don't get in trouble with revealing any of the other kind of stuff, which of course we don't need the whole world to know on YouTube, but I think what we did now is not classified. It's the kind of stuff you could learn, out of textbooks in colleges.
Yeah, go and build one in your shed, blokes. No, please don't. Well, thanks, Dan.
Some people have.
Yeah, keep your hands out of the beam, please.
Yeah.
All right. Thank you very much and keep in touch.
Thanks, we will. And thanks for the opportunity. It's a humbling experience to be asked by you to give a presentation. So
it's an honor, sir. Thank you.
Wow, Dan Isbell, thank you so much. I am in such a privileged position to know you and for you to share that trust in me and this channel to actually tell us about the things that you actually know about. It's an honor. Thank you for your service and thank you for sharing this very special lecture with the public today. Because of you, Dan, I can genuinely say the truth is now out there. Thank you.